Distinguished Crafoord laureates, presidents of the Royal Swedish Academy of Sciences and of the Crafoord Foundation, ladies and gentlemen, it is a privilege to have been asked to introduce the work by Eugene Parker, and I will give some of the background for his award of the 2020 Crafoord Prize in Astronomy. The statement is for pioneering and fundamental studies of the solar wind and magnetic fields from stellar to galactic scales. And arguably, the most, momentous part of this has been the realization of the existence of a solar wind. And perhaps the most, key paper of this was published in Astrophysical Journal back in 1958. And dynamics of the interplanetary gas and magnetic field. What brought him there? Well, if you look at the introduction of that paper, on the very first words, he quotes Biermann from early 1950s, who pointed out something about comets. And what are comets? Well, comets are these icy dirt ice blocks coming into the inner solar system from further out, heated by the sun and evaporating gas and dust from their cores. Many comets are seen to have two tails. One whitish tail that is reflected sunlight, that is basically dust, and a tail that is usually bluish, which is gas. What Biermann had realized or noted that it looked as if this gas tail was changing with time, as if some wind was blowing and molding it. That was one realization, a suggestion that there is something out there in space that is physically changing these comet shapes. The other background is that the solar corona, is the hot outer part of the solar atmosphere, which you can see at rare occasions with the naked eye when there's a total solar eclipse. And there's a sequence of the latest solar eclipse as seen from Antarctica just a few months ago. And when the moon has covered the sun completely, you can see these outer parts. That the solar corona is hot is actually quite peculiar. Here is from a paper by Eugene Parker himself, exploring the innermost solar atmosphere. He points out that the coronal, backgrounds of understanding the corona is the realization that the corona is extremely hot. I mean, this is peculiar because the solar surface, well, it's hot enough, but it's not that hot. And a lot of this work was done by Bengt Edlén, who we know here in Lund in particular. He was a professor of atomic physics here for many years. Before that, he was in Uppsala. And he was one of those persons who identified the high temperature of the solar corona. And here he is seen with his then mechanical, calculating machine at those times. What Eugene Parker could combine then is understanding that the nature of a hot gas, here he has some models for his early paper, corona of 500,000 degrees, 1 million degrees, 2 million degrees, how that would be, expanding into the space outside the sun. And with this expansion, it would carry magnetic fields. It would be carrying magnetic fields out into space, and they would be following, or they would be influenced by the rotation of the sun, like a garden hose when you're swinging something around, and penetrating the space between the planets. Now, that at that time, of course, was very unusual ideas. And what often happens with great discoveries, the scientist wants to publish a paper, but of course it is rejected. And of course, this also was the case here. And that, of course, is part of the great discoveries. Many great discoveries do include an element of a surprise, something unexpected. And one way to see how this unexpected thing grows into accepted is to things like metrics, like the citation counts of this particular paper from 1958. The first several years, this is number of citations per year. Well, yes, it was noted, but the real impact comes only 50 years later. And that, for many great discoveries, is something that shows the difference between just a conjecture and something that is really significant. Unfortunately, Eugene Parker is no longer with us. He passed away just last month, but a few of us had a chance to meet him, maybe not very closely, but meet him at some events, at conferences and others. And not long ago, some colleague pointed out what must have been the first occasion when I had a chance to meet him, a summer school or a conference in the south of France at Château de Bonnat back in 1980. And here, Gene Parker is in the middle of the team, surrounded by several people, several of which have been, say, continuing careers in fields of solar stellar physics since. But the legacy of his work, of course, lives on. And what is maybe one of these, say, broader legacies is that, yes, we know we are living next to our sun, of course, but it's not only that. We're actually inside the sun, or at least inside the solar atmosphere. We're inside the solar wind. And the solar wind is affecting us, affecting the Earth, and is also protecting us from the charged particles coming from the Milky Way galaxy. And together with the solar wind, it forms the astrobiological ecosphere that is supporting life here on Earth. So, unfortunately, Gene Parker is not here. But we have Dr. Nicole Fox. She is the director of the Heliophysics division at NASA headquarters in Washington, D.C. And heliophysics, that is what concerns the sun, the solar wind, and the interactions with the Earth. And so the study of the solar wind goes on. And what is the status, what is the cutting edge of this? We'll hear now from Dr. Nicola Cox, and so please, the floor is yours.
Good morning, everybody. I'd like to start off by congratulating the winners of the Crafoord, the other laureates who are here today. I am obviously extremely humbled to be giving this presentation on behalf of Gene Parker. So I'd like to also thank members of the Royal Academy and the Crafoord Foundation. And I would like to also a big thank you to Gene's family who have trusted me with this incredible honor. And so they're here today, Joyce Parker, Gene's daughter, Eric Parker, Gene's son, his wife Susan, and his grandson Miles Lowe and his wife Michelle. So I hope you get a chance to meet with them in the break. As the introduction said, I am the director of NASA's Heliophysics division, and as such, I get to actually manage and look after a lot of missions, 20 that are actually up in orbit right now and another 14 that are in development, all of which are really studying science that was driven by Dr. Eugene Parker. And so heliophysics is indeed the study of the sun, our closest star, everything from the very, very center of the star all the way out to the very edge of its influence and indeed beyond. And so here you see a very familiar looking planet, the Earth, and you can see that our magnetic field is protecting us from all of this stuff coming from the sun. If we go up and I take you to the poles of the sun, you can look down on the poles and you will see that atmosphere starting to spread away in a spiral shape. That spiral known as the Parker spiral, because of course Gene predicted that would happen. Then we go to the very edge. So this is now the very edge of our sun's influence. This is where the solar wind stops and it meets interstellar space. This is yet another prediction of Gene Parker that in fact our solar wind would form a protective cavity around not just our planet and our star, but our whole solar system. So as we are orbiting around the Milky Way, the solar wind actually protects us from the vagaries of interstellar space, from particles, from dust, from cosmic rays coming from us. And so we have a pretty nice life here because of the solar wind. But so here is just a picture of Gene, just to tell you about maybe his early career. So Gene's early career coincided with the beginning of the space age. He started publishing his papers. His really seminal paper in 1958, of course, coincided with the launch of Explorer 1, when we actually discovered that space wasn't empty. It was actually pretty interesting. And so because of that, we continue to study it. But not only did he, and here you can see Gene honored holding his Crafoord medal, which we were able to, thanks very much to the people from the Crafoord Foundation, were able to actually give to him in Chicago in November of last year. And you can also see Gene, if this pointer works, wearing his Parker Solar Probe pin. And if you want to recognize the Parker family, they're all wearing them too. And so Gene obviously won his Crafoord Prize, but he won many other awards too. And you can see in 1989 here, President Bush presenting him with the National Medal of Science. He also won the Kyoto Prize. He won the James Clerk Maxwell Prize in 2003, and he won the Hannes Alfvén Prize in 2012. He was a member of the National Academy of Sciences in America. He was also a founding or a legacy fellow, of the American Astronomical Society and also the American Physical Society. And he was a very nice guy as well. So in addition to winning all of these awards, he also authored 4 books and over 400 scientific papers, most of those just under the single author, which is really, really unusual. But really, to understand Gene and to sort of understand his ingenuity, his inventiveness, his creativeness, and his stubbornness, and maybe, well, his geneness, you really have to understand kind of some of his early life experiences and you know what those did, the type of things he saw and what how they affected him. So Gene was born June 10th, 1927 in Houghton, Michigan. You'll see here a sort of pretty typical view of a typical town in 1927. His parents, Glenn and Helen Parker, and his grandfather here, you can see Fred McNair, who was actually the president of the Michigan Mining School. So he came from a very great lineage of scientists and engineers. His father an engineer, his mother getting a degree from Caltech? No, wrong one. Stanford, thank you. So in the early in Gene's life, he was born the same year as the Mississippi flood. I've got Michigan on the brain. He also, in his early years, experienced the Great Depression and lived through World War II. And these are all very significant. Anyone who lived through those kind of things was very profoundly affected by that. But when Gene was 16, he decided he'd had enough of spending his summers in suburban Detroit. And so he went to the state capitol and purchased a piece of tax-delinquent land for $120, which he'd saved up from his summer work. And he bought this. This was up, not very close to where they lived, way up by Mackinac in the northern peninsula of Michigan. And over 3 summers, he and his younger brother and a couple of friends would go up, and they actually built a log cabin. The only thing on this land was trees. They knocked down the trees and built a log cabin, which still stands today. But just maybe to give you an idea of what Gene went through, gas or petrol was still highly rationed at the time, so he couldn't get a ride. So he and his friends rode 300 miles on their bikes to get up to do this cabin. So really, having a paper rejected was nothing for Gene after all of this that he'd gone through. So his early education, he went to Michigan State University, where he studied physics, and then he moved out west to Caltech, where he did his PhD. And you can see a nice picture of him there at Caltech. And he did a wonderful PhD on interstellar dust and gas. And so it was basically an investigation into the statistical properties of the mechanics of gas and dust that make up interstellar space, how they move, how they flow, how they change. And it really struck me, you know, he did this in 1951. Now, of course, I would immediately think, I'm an experimentalist. I use real data. I would get Voyager data, and I would get IBEX data, and I would put that together, and I'd study it. Voyager hadn't even been launched then. Nothing had been launched. Even Explorer 1 hadn't been launched. And so to do all this statistically is just incredible. But fortunately, even though he did his PhD in interstellar, the medium, Gene always loved and was fascinated by the sun. And thank goodness for us, he was really fascinated by the sun. And he followed people have always been fascinated by the sun. Ancient Babylonians carved eclipse images into stone tablets. Renaissance astronomers looked through telescopes and tracked sunspots, those dark splotches on the sun. And then eventually we took to space and we were able to study our star in unprecedented ways. And of course, we've always been sort of limited by the scope of our tools. But being human, we just build new tools and we build more and more sophisticated machinery to allow us to do more and more in-depth study of the sun. Gene was, even before we had launched space-based probes, Gene was fascinated by the sun. And once he'd done his PhD, he went for a short time to a university in Utah and then on to the University of Chicago. Straight out of finishing his graduate work, he wrote amazing papers. He actually wrote about the formation of sunspots. He wrote about the solar dynamo and how the sun's magnetic field actually drives and powers the sunspots. He actually wrote about the effect of the sun and how it would cause geomagnetic activity at Earth. In a sense, he discovered space weather before anyone else had even thought about space weather. He went on, he talked about solar flares and predicted that solar flares would actually have accelerated particles associated with them. And then he went on after that, as if that wasn't enough, to study magnetic reconnection. And he was at a conference and Peter Sweet was presenting a paper on how if you brought two plasmas together that had opposing magnetic fields associated with them, that diffusion could occur and actually reconnection would happen. But he hadn't really fully developed the idea. So Gene, on his travels home, just knocked out the relative scaling factors for this. And they published a paper together, and it is still known as the Sweet-Parker effect. But in 1958, and this is in Gene's own words, he solved 4 lines of algebra. That is how Eugene Parker described finding the solar wind. He actually said to me, all I did was solve 4 equations. So he solved 4 lines of algebra. And it was all predicated on the Biermann study of the comets, which was so beautifully described to us. Biermann was actually visiting Chicago and he was meeting with John Simpson, who was Gene's boss at the time. And he presented exactly what you just saw, that the comet tails were always pointing away from the sun. And he actually said, well, there must be something moving out. It's some sort of, he called it corpuscular radiation. Now, John Simpson kind of dismissed it out of hand and said, maybe something comes out occasionally, but it's not coming out all of the time. And he also cited a famous scientist at the time, Sidney Chapman, who had said that much like the Earth's atmosphere, the sun's atmosphere would be static. And so John Simpson, had dismissed everything, but he passed all the work on to Gene Parker and said, see what you think about this. So Gene studied it. He solved his 4 lines of algebra, and he came up with different sort of solutions for these 4 lines of algebra, 5 of which were physically not possible, but the 6th one was. And I'm actually going to, I don't usually use notes, but I want to make sure I get this quote right, because I love this. This is from a paper by Kane in 2009. So Gene Parker went to John Simpson and said, John, Biermann is right and Chapman is wrong. So John Simpson said, Eugene, what is your basis for saying this? Well, my calculations show that the sun's atmosphere is not only not static, but it's highly dynamic. And with millions of degrees of coronal temperatures, the whole place would be boiling, and some flow would come out, sometimes more, sometimes less, but never zero. And I, Eugene Parker, would like to call it solar wind. So John Simpson said, so what do you propose to do? Write a paper or something? Gene said, well, yes, unless the university prohibits it. John Simpson replied, no, 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 no. We're very open-minded here. Do what you like. Publish what you like. But for heaven's sake, don't put my name on it. Wonder if he ever regretted that. So several journals did indeed reject this paper. But luckily, an editor did intervene. But one of the referees went so far as to actually say, if you're going to publish in this area of science, you might want to go to the library first. And Gene told me this, and he said, oh, Nikki, that was the nice review. So fortunately, the editor was Chandra Sarkar, who was also at the University of Chicago. And he was, really kind of enjoyed the controversy. And he said, Eugene, I think this is a ridiculous idea, but I don't want to see it killed, so I'll publish it. And certainly, Gene got a lot of maybe ridicule's too strong a word, but a lot of pushback and a lot of, goodness, what is all this about, from colleagues. But then just a few years later, in 1962, the Mariner 2 spacecraft, on its way out to Venus, did indeed sense the exact solar wind that Gene had predicted. And so the rest is kind of history. But one of my favorite comments that Gene made was, if you do something new or innovative, you should expect trouble. Of course, Gene did not stop there. Goodness, no. In addition to discovering the solar wind, he also correctly predicted that the solar wind would create this large bubble around the sun, which we call the heliosphere, and you saw that in the initial animation. And that really changed the course of science with his work on magnetic fields everywhere in the cosmos. He also talked about the fundamental stellar forces that he described very clearly in his work. And of course, if you can explain what happens at our star, it is highly applicable to what happens at other stars, which means that not only does his work tell us about life here, but it also can tell us about thousands of exoplanets and maybe eventually how we would find habitability on exoplanets. The solar wind is also the things that drives all of our space weather here at Earth. It causes beautiful aurora, which, where I live in DC, I don't see them very often. You get to see aurora very often. I'm very jealous. But that powers the aurora, that causes a lot of issues for power grids, for GPS, for all kinds of technology that we rely on. And so all of the work that Gene has done really tells us about space weather. So lots of great things that Gene has done. But maybe, I'm not going to say it was his proudest achievement by any means, but the thing that maybe I am the most proud of is because of something that Gene did. And that is causing us to have flown now the Parker Solar Probe mission. And so I mentioned 1958 that this paper came out, and I also mentioned John Simpson. Now in 1958, we had just discovered space was interesting. So interesting that it was decided that we needed to form a national agency to actually study space. We know it now as NASA. A committee was formed by the National Academy to actually give NASA its charter to say, what are the big goals? What are the big things that we want to do with a space program? That committee was chaired by John Simpson and co-chaired by James Van Allen, actually. And they put together a list of 14 missions that would be, really big goals that we wanted to do. One of those missions was a solar probe. So even though John Simpson didn't want his name on the paper, he recognized how important it was to go and study close to the sun. And so in 1958, solar probe was first proposed as a mission. It took 60 years for that to be launched. At no time did anyone think it's not worth it. It remains the highest priority mission in all of our decadal surveys, all of our documents that we have from the National Academy telling us what we should do. But we did have to wait 60 years for technology to be able to support this daring mission to go into the sun's corona. So this is just a look at some. Believe me, I could give you a 4-hour lecture on all of the technology behind this spacecraft, but don't worry, I won't. But some of the things that are really important is our heat shield on the front of the spacecraft there. It's an unusual looking spacecraft. I love it so much, I wear it around my neck, by the way. But this is a 8-foot wide heat shield. It's about 3.5 inches thick. It is made of a carbon-carbon composite. It's a bit like a graphite epoxy that you would find in your tennis racket or a really nice bike. Very light, but very, very durable. In the center, it's two phase sheets together. In the center, there is some carbon-carbon foam, which incidentally is now being used in bone replacement therapy. And on the front, it actually looks orange here. That's actually a white coating. It is a plasma sprayed alumina material that was actually designed specially for Parker Solar Probe. It's plasma sprayed because it has to be totally flat. You can't have any bumps or raises in it, otherwise you get thermal gradients across the front of there, which would be very bad. So this heat shield faces temperatures of about 2,500 degrees Fahrenheit or 1,400 degrees Celsius. Now it is traveling through 3 million degree plasma. That is the heat of the corona. But the corona is not particularly dense. And so we don't get a lot of heat transfer into the heat shield itself. And so when I say it only has to cope with 1,400 degrees, at least it's not 3 million degrees. The heat shield remains pointing to the sun, and all of the instruments on the main body of the spacecraft are actually at a temperature of about 30 degrees, so a little bit above room temperature. So 1,400 degrees on the front, 30 degrees here. The heat shield itself is held in place by a titanium welded structure. We cannot have any of the heat that the heat shield does experience conducting into the spacecraft. And so the whole heat shield is just held in place by 6 tiny carbon bolts. Again, to make sure we don't bring any heat in. And they're on kind of like a shoulder joint. Because as this heats up and then it gets very cold on the other side of its orbit, we know that the heat shield will actually kind of change in shape. And it will sort of bevel. It may even do like a potato chip, like a Pringle. And it was impossible to model totally what that would do. And so we actually had to design it to cope with the worst possible distortion. I should also note that Parker Solar Probe goes very close to the sun on one side, getting to, eventually we'll get into about 6.2 million kilometers away from the sun's surface. If I put the sun and the Earth a meter apart, Parker Solar Probe would be about 4 centimeters for the sun, just to put that in scale for you. So it gets very, very cold when it comes out around the planet Venus. So we use Venus for gravity assist maneuvers. And so it gets very, very hot and then very, very cold. And it does that at least 24 times. It's a 24 orbit mission. And if you think of taking any material and heating it, superheating it, and then supercooling it over and over again, most materials will change their property. They'll either become kind of elastic or they'll become brittle. We can't have that. So we had to design something that would be able to take not just the incredible heat, but the incredible variation in temperature. One other thing that we did with Solar Probe is we use solar panels to heat to power the spacecraft. And most people look at me like, well, what's the problem with that? You're going to the sun. Surely solar, I mean, why wouldn't you use solar cells? But any of us who've accidentally left our iPhone on the front seat of a car on a hot day know that the one thing that any kind of electronics like this, they don't like to get hot. And so actually cooling these solar panels became a major challenge for us. And so what we do is we actually cool it with water. And in between each of the solar cells themselves, like veins run between them. So we run water through the solar panels continually. The actual structure that holds the heat shield in place has radiators on it that actually gets rid of all of the heat from the water from the solar panels, and then it just sort of recirculates. Also, the solar panels are completely articulated, so they stretch all the way out when it's close to Venus, and then they tuck all the way in when it's close to the sun. And it's maybe, again, to give you scale, there's one tiny row of solar cells on the very tip of that outer wing. When it's close to the sun, just that one row of cells produces the same amount of power as the full wing does when it's out around Venus. So it kind of gives you an idea of how close we are. And then just some state-of-the-art instrumentation. We actually have one instrument here. I refer to it as the bravest little instrument because it does not hide behind the heat shield. It kind of peeps out around the side and is in the full solar atmosphere. And so it actually has to deal with all of the heat and all of the changes. And so we had to use some very special materials and a very special way to actually suspend all the wiring. So the wiring is in sapphire crystal tubes. The materials that we use to make this particular cup are molybdenum, molybdenum, and all kinds of very long, expensive materials that we had to use. So that was these are just some of the challenges. I'll also note that she is probably the most independent and most autonomous spacecraft ever flown. If you think, it takes light 8 minutes to get from the sun to the Earth. And so if she has a problem, there's no way we can get the command back at Earth, discover that she has a problem, send a command back and fix it. So the spacecraft is fully automated. There are little sort of sun sensors all around in various places around the spacecraft. They should never see the sun. If one of them sees the sun, the spacecraft knows what to do. It will fire thrusters, and the name of the game is always to have this heat shield in place. Now, if you think in 1958, if you wanted to, just think about the phone call. If you wanted to make a phone call, you had a phone rotary dial on the wall. Now we all walk around with our iPhones. And so if you just think about the leap in technology that in that 60 years, the type of commanding, the type of computer smarts that this spacecraft has would have taken city blocks worth of buildings to do that kind of computing power. Now it's in a chip about this big. So that's why it took us 60 years. But despite all the history and despite everything that is so wonderful about this spacecraft, the thing that makes it so special is it is dedicated to Gene Parker. And you will see here on the spacecraft is the dedication to Gene. This was the quote he gave me in July 2017 when I asked him to put a quote on the spacecraft. It is the first time that NASA had ever named a mission for somebody during their own lifetime. And so not only did they name it, but Gene also got to see the spacecraft launch as well. Now, it is highly rare for anyone to win a Crafoord Prize, but only 20 people have had a NASA mission named after them. So this is really rare. So this is the spacecraft in all her glory. There you can see the heat shield on the top there. She actually stands just 3 meters tall from tip to stern. So she is actually a very small spacecraft, and you can see how we tuck in all of the solar wings. So this is obviously the animation of the spacecraft coming off the launch vehicle. And then separating. We had a kick stage, upper stage motor that will fire, and that gave her all the delta V that she needed to be able to escape from the pull of the Earth. The one thing we don't want to do with Solar Probe is in any way get pulled around the sun with the Earth. We don't want to have any angular momentum from the Earth. And so Parker Solar Probe is moving incredibly, incredibly fast. Once launched, you'll see those lovely solar wings come out near the Earth. They're out at full stretch to be able to power. And then you'll see some of the instruments that deploy. Obviously, they're all tucked up for launch. That's the magnetic field. And these are the radio wave antennas that will come out now. Yes. So I knew they were going to. Anyway, so we fly past the planet Venus. You can see Venus there. Venus here, sorry. We use the Venus to trim the orbit. So you may be familiar with some spacecraft that use gravity assist to actually speed up. We're very generous with Solar Probe. We give energy to Venus. We use Venus to slow down a little bit. We actually trim our orbit to allow us to do very tight petal-shaped orbits, very close to the sun, flying through the corona on one side, and then on the other side, using Venus. We actually will use Venus 7 times to be able to do these gravity assists. So we walk closer and closer into the sun. At final closest approach, I think I already said, but Parker Solar Probe will be about within 6.2 million kilometers of the sun. She's also broken an awful lot of records, traveling at record speeds. At her top speed, she'll be just shy of 700,000 kilometers an hour. That's about 200 kilometers a second. So imagine the speeding tickets that she would get. So that's solar probe. No, there we go. So this is just a couple of images of the launch. We launched on a Delta IV Heavy, a beautiful, very large rocket. As I noted, even with all the awesome power of the Delta IV Heavy, we actually had to have an upper stage motor to give us that final kick stage. So this is the evening of the launch. And in fact, myself and members of the Parker Solar Probe team stood about here and said goodbye to our girl before she launched into space. I'm not sure if you can see it very well on here, but there's a bright spot up here. That's actually the planet Venus. And so we all thought it was very fitting that not only were we saying goodbye to Parker Solar Probe, but her first stop in space was indeed Venus. I had the pleasure of standing with Gene Parker and his family at the launch. And one thing that really sort of stuck with me was when Solar Probe launched, he actually said to me, "It's so sad, it's not coming back." And it was a phrase that at the time I was busy and I was stressed and I was doing all these other things. But when it had quietened down and everybody else had left and I was at Kennedy Space Station on my own, I thought about these words. And it actually moved me so much that I drove out on my own. It was by now 6 o'clock in the morning. I drove out to an empty launch pad and watched the sunrise and maybe shed a few tears for Parker Solar Probe. It's amazing when you work on a mission for so long, the spacecraft itself becomes like part of your team. You know, the spacecraft's the Voyager, they're the explorer, they're the ones that are going to do everything. But it really is sad that they're not going to come back. So not only did Gene get to watch the launch of his namesake spacecraft, but he also got to see groundbreaking results come back from the spacecraft. And I know you're going to hear a lot, if you're coming to the symposium tomorrow, you'll hear a lot about all the different results. So I'm just going to hit on a couple of them in the time I have remaining. So in fact, the very first orbit that we had with Parker Solar Probe, we had unexpected results. So we're not particularly close to the sun at the beginning. We use those gravity assists to take us closer and closer as the mission goes on. But on our very first orbit, we discovered these really, really, really weird magnetic field signatures. Now, I mean, you know, we're all scientists, so you're not going to think this is as funny as a normal general audience would. But we put up a plot of magnetic field at the American Geophysical Union meeting in Washington, D.C., and there were audible gasps from the audience because of this wiggly line. And so, you know, at first we thought, golly, is the magnetometer not working? Because it's seeing all these different signatures. Or are we, basically we were seeing these incredible reversals in magnetic field, really, really, really tight amplitude fluctuations. And we thought, you know, maybe we're sitting at the heliospheric current sheet, so where you've got polarity from one pole on the top and polarity of the other pole kind of underneath. Maybe the spacecraft's just sort of, you know, the current sheet's just going up and down over the spacecraft. But that still didn't quite make sense. So we had to wait a few more weeks because it's challenging to get the data down. There's this large glowing star between you and the spacecraft. You have to wait for exactly the right time to get your data down. So we had to wait to get the plasma data down to be able to sort of match it. And when we got the plasma data down, we realized actually we're not seeing major reversals in the field at all. We could see when we actually crossed the heliospheric current sheet because the phase space density or the sort of the direction of the plasma on the magnetic field made big changes when we actually crossed the current sheet. But when we were seeing all these tiny fluctuations, there was no change in the direction of the flow of the plasma. So what that meant is we were seeing sort of S-shaped curves in the magnetic field itself. And if you think it's kind of hard to twist a magnetic field, we still don't know why the magnetic field is twisting like this. This will be the future of our exploration. But we saw these S-shaped curves that were tight and then were relaxing. And so even on our very first orbit, we start seeing a way that major energy could be being deposited into the solar corona. And so now you start seeing reasons that maybe the corona is so much hotter than the surface of the sun. We definitely have smoking gun for this is how we think a lot of the energy is getting into the solar wind. It's not simple turbulence. It is very well organized. These flows, these S-shaped curves are kind of ubiquitous in the corona. They tend to happen in clumps, and then they're sort of separated by slow solar wind. So that it's a very organized structure, and there's already been, I think, more than 20 or 30 papers written on these structures, many more to come. As we get closer to the sun, we actually expect to start seeing them getting less and less as we get closer to the sun. The other thing, the big accomplishment for us last year was actually, it's almost a year ago, on April 28th of 2011, we actually crossed the Alphane surface. This is, for those of you maybe not so familiar with the workings of our particular star, very close to the sun, the whole magnetic field of the sun rotates with the sun. So it like rotates kind of as one rigid body. There is a place, it's called the Alphane surface, where the solar wind gets so energized that it can break away from the giant pole of the star, gets accelerated, and moves out to the very edge of the heliosphere, the solar wind. When this happens, it basically grabs the magnetic field with it and takes the magnetic field out. And so now you've got sort of two populations, one that is in a rigid body and the other that is super accelerated and accelerating out towards the edge of our heliosphere. It's a very critical region for us to sample, and we'd actually thought we would have to get a lot closer to the sun, maybe within 10 solar radii, to be able to really see this. But we actually did this at about 18.8 solar radii above the sun's surface, and that allowed us for the very first time to fly through the sun's corona. It allowed us to sample both the magnetic field and the plasma, and also the wave structures that are in there. And with that, we hope to actually be able to start really explaining why this incredible acceleration happens. As I already noted, everything that we learn about our own star teaches us more about other stars. So it's highly, highly important. And I wanted to this was something that, sadly, I never got to show Gene this particular movie. But this is, if you're riding with Parker Solar Probe, would be what you are seeing. And you are seeing the solar wind. You'll see some beautiful structures. These are coronal mass ejections. There's a lovely one there coming out. And you'll see another one here. And then what we call a cannibal event, which is 3 quick ones that kind of eat one another a bit like a Pac-Man. Here we go. There's 1, 2, 3. And they then form a big coronal mass ejection coming out. So one thing I can tell you is our star is definitely waking up. We are out of solar minimum and moving up to a very active star. But the first time I was able to show Gene one of these types of movies, he actually looked at me and said, "So that's what the solar wind looks like." And just to sort of, it's a little bit of bonus science or extra science that we got from Parker Solar Probe, and I just think this is very fitting because I mentioned that it was Mariner 2 that proved the solar wind existed. And so it seemed only fitting that a solar wind probe bearing Gene Parker's name would also give us groundbreaking science of Venus. And what you're looking at here is the very first images of Venus taken with visible light. And so our camera, while we were flying past Venus doing our gravity assist, was able to actually capture these images. And you're actually looking at, and so this is unusual because they're able to get through that dense Venusian atmosphere to be able to see this. And so you're kind of looking at thermal emissions from the night side of Venus, and they glow, they sort of faintly glow in visible light because the temperature there is in excess of 745 Kelvin, so it's pretty hot. And so you can see some structure. These are the highlands where it's a little higher up and then a little bit cooler, and the brighter spots are the lowlands where it's warmer. But you can also see the Magellan images here, just to sort of give you the context for that. But it was just such a nice thing to see Parker Solar Probe not only telling us about the solar wind and the sun, but also giving us groundbreaking science at Venus. And so I'm going to finish unashamedly with my favorite pictures of Gene. And this is, you can see his eyes lighting up. I am telling him the science results from Parker Solar Probe. This is when we renamed the mission for him and he received his own model. But you know, it was just an amazing opportunity to get to know Gene and his family over the last 5 years. Here I am with Gene, introducing him to his spacecraft. And yes, I did say, Parker, meet Parker. And Gene was just amazed at, you know, you stand in front of a piece of technology that is going to go and do the work that you wanted to do 60 years ago. And he was very humbled by just, you know, the sheer magnitude of work that goes into a mission like that. And you can see many great images of Gene watching the launch there. This, of course, when we were able to give him his Crafoord medal back in November. And so I'll leave you with the thought that, like a loving dad does with his children, Gene Parker hoisted humanity onto his shoulders and he let us touch the sun. Thank you.